Okay, Sir Barnabas, I think we're ready.
What?
Oh, yes. Yes, of course, Sir Barnabas.
Hey, Noah. What's up?
Excuse me for a moment, Sir Barnabas. Oh, hey, Pete. Not much. How are you?
I'm fine, but, what are you doing?
Well, Sir Barnabas and I are...
Hold the phone. Sir Barnabas?
Yeah, I'm sure I've mentioned him to you before. Sir Barnabas Cheese and Crackers. He was my imaginary friend when I was a kid, and I thought it'd be fun to hang out with him again, so I found his number.
Wait, your imaginary friend has a phone number?
Well, it's an imaginary number, of course.
Oh my God, why didn't I see that coming?
So, Noah, imaginary numbers are super interesting and actually less imaginary than you might think. So, hey, I've got an idea. Why don't we leave Sir Barnabas over there on that side of the imaginary line while we head over here and maybe record an episode about these imaginary numbers? Okay, but why? Our episodes are always about real things and real math. Why would we want to do an episode on imaginary numbers? Can they even be used in any real world applications with actual non-imaginary math?
Okay, so the first thing I want to know is, why are you so certain that there's such a thing as imaginary math and real math? Like, what makes you think this is so super imaginary?
Probably the word imaginary that mathematicians have tacked on to the beginning of the term imaginary numbers. I mean, what else could imaginary mean?
Well, you're talking about numbers like the square root of -1, or really the square root of any negative real number. And you're saying those have been called imaginary numbers. They must be imaginary.
Well, I know for a fact that they don't actually exist as legitimate quantities. There is no number that when you multiply it by itself, you get -1. If you multiply two positives together, you get a positive. And if you multiply two negatives together, you get a positive. There's no way to multiply any number by itself and get a negative answer.
Yeah, you just hit on pretty much the stumbling block that mathematicians ran into for, I don't know, like 1,000 years. This notion that any number, when multiplied by itself, produces a positive result, with the exception of 0, of course, right? 0 squared is 0. And that was a stumbling block for many years. But do you actually know where the word imaginary comes from in imaginary numbers?
Linguistically speaking? No, I assume it has the same root word as imagination.
Well, right. I mean, specifically, who coined the term? It actually came from Descartes back in the 1600s. And very specifically, he was talking about solutions to polynomial equations and saying that some polynomials, when you plugged in an imaginary or a complex number, would produce 0 as an outcome. Well, he wrote, for any equation, one can imagine as many roots as its degree would suggest, but in many cases, no quantity exists which corresponds to what one imagines. So, take a very simple equation like x squared plus 1 equals 0. So Descartes is saying, well, you would expect two solutions there because the degree of that polynomial is 2, right? Its highest power is 2. But you can't find two real numbers that, when plugged in, solve the equation.
Okay, so I see what you're saying, and I see that the term imaginary didn't really come from a place of someone saying they're fake or unreal, but it came from this quote from Descartes about when you imagine the different solutions here, yada, yada, yada. But I mean, come on, you would still say that imaginary numbers are less real than non-imaginary numbers, right?
Well, I wouldn't say that personally. I think that they're a lot less mysterious than you might think. And I think it really is the name imaginary that makes all of this seem so remote or fabricated. But really, the square root of -1 is actually very easy to understand.
Okay, well, explain it to us.
So imagine that you're standing at the origin of the XY plane. So it's a very familiar location, right? Every point in this plane has an X and a Y coordinate, and we know how to move around it. We understand how the plane works. So if you're standing at the origin and you take one step off to the right along the x-axis, where do you end up?
At +1.
Yeah, at +1. Strictly speaking, the coordinates are 1, 0, but we all understand that, oh, that corresponds to the number x equals 1. Great. And if you take a step left from the origin, where do you end up?
-1.
-1. Yeah.
Sorry. -1, 0.
Yeah, right. -1, 0. Now, standing again at the origin, take one step up along the positive y-axis. Where are you then?
Then I would be at 0, 1.
Yeah, and also you would be at the square root of -1, because that's where it is. At the point 0, 1, 1 unit up on the y-axis in the xy plane. Boom, we're done. We found it. Case closed.
Wait a minute. I don't understand this at all.
Hold it. What is this? Are you trying to trick me?
How is the square root of -1 a coordinate 0, 1 on the graph?
Okay, so I think there is some background that we should share here. So instead of the xy plane, let's just focus on the x-axis, okay? What does multiplication by -1 do to the real number line?
Well, let's say I'm at 5 on the real number line. If I multiply it by -1, I go to -5. If I start off at -5 and multiply by -1, I go to 5. So I guess the best way I could explain it is the absolute value of the amount that I'm on stays the same, but my polarity, for lack of a better word, changes, positive or negative.
Right. And so can you think of a geometric operation that you could perform on the real line that would effectively do the same thing as multiplying by -1?
Could I flip it horizontally? Like I stay in one place, but the axis kind of rotates about the origin underneath me?
Yeah. And how far would it have to rotate to do that?
It would have to rotate 180 degrees around.
Okay, perfect. So that's what multiplication by -1 does. All right, now, we know if it exists, the square root of -1 is something that when multiplied by itself yields -1, right? That's in fact what we mean by the square root. So what would I have to do to the real number line so that if I did the operation twice in a row, it would end up rotating by 180 degrees?
I'm not sure, but I think what you mean is if you rotated it 90 degrees twice, that would be the same as rotating it 180 degrees.
Yeah. And so now let's just do it once and stop for a second. So you take the real number line, the x-axis, and you rotate it 90 degrees. What does it become?
Well, now it lines up with the y-axis. Now it's just the y-axis, right?
Yeah. And so we are imagining that we did some operation that took us from the x-axis up to the y-axis. If we were to repeat that, the y-axis would rotate down to the x-axis again. However, that polarity reversing effect would have taken place. 1 would have gone to -1, right? That's what multiplication by -1 does. So multiplication by the square root of -1, which I'm suggesting is nothing other than a 90-degree rotation, should therefore take the number 1 and rotate it 90 degrees, and it ends up at the square root of -1, which is 1 unit above the origin in the xy plane.
Wow. I get what you mean.
Have you never heard that before?
No, I've never heard that description before. And I didn't know where in the world you were going when we started talking about a coordinate plane, but that's a cool way to visualize it.
Yeah. And earlier you were mentioning I'm standing on it and I'm going to rotate it under me. You know, it doesn't really matter how you do this rotation. The point is that if you were to take a line and rotate it around a fixed point, it would trace out a plane. And what I'm suggesting is whatever plane you end up tracing out, that's the one we want to look at. And I want you to stop at the halfway point at 90 degrees. And that's what we're going to call the imaginary axis, as it is known in the world of complex variables. All right. You know, what I think is cool about the imaginary axis is that it was a hidden dimension there all along, but we just didn't know it. And now it's like, oh, duh, there it is.
There it is. There it is. There it is.
it might be, oh, duh, there it is for you, but I had no idea until you just explained it. Yeah, I've used the word complex now a couple of times, and that's a little bit distinct from the word imaginary. Have you heard that expression before? Complex numbers? I have definitely heard that expression before, but I would be hard pressed to tell you what the definition is right now. So if you take a real number, which is like one of those numbers on the x-axis, and you take an imaginary number, which would be one of those numbers on the vertical axis, and you add them together, it's going to take you somewhere. And that somewhere is going to be a combination of the x and y components. So that combination is called a complex number. Okay, how about we do an example so we can visualize what's going on? Yeah, sure. So let's suppose we have the real number x equals 2, and we want to add it to the imaginary number 6i, and that just means 6 times the square root of -1. So the result is 2 plus 6i, and we call it a complex number because it has both a real and an imaginary part. Okay, but what should we be picturing for this number? Like, where's it located on the number line? Well, it's not a number line, it's in the plane. So x is 2 units to the right of the origin, and 6i is 6 units above the origin. When we add them together, we end up at the point that is both 2 units to the right and 6 units up. Oh, I see. So it's like there's a rectangle sitting in the first quadrant with one corner at the origin and the other corner at the point 2, 6. Right. In fact, you have just given the definition of a complex number. A complex number is just an ordered pair of real numbers. Huh. I gotta tell you, Pete, that doesn't sound all that complex. Well, okay, but it did take some ingenuity for us to arrive at such a simple definition. In fact, this definition wasn't introduced until 1831 in a paper by the Irish mathematician Hamilton. All right, but now that we see how simple the definition is, why are they called complex numbers? So the terminology came from Gauss, and I think he used it to mean compound, as in consisting of more than one part. Okay, gotcha. But what's super interesting to me is he did not like the name imaginary. And I dug up a quote about this because I thought it was so interesting. And here's what he wrote: that this subject, imaginary numbers, has hitherto been surrounded by mysterious obscurity is to be attributed largely to an ill-adapted notation. If, for example, +1, -1, and the square root of -1 had been called direct, inverse, and lateral units instead of positive, negative, and imaginary, or worse yet, impossible, such an obscurity would have been out of the question. That kind of makes me realize that the question I asked right up at the start of the show was a direct result of what Gauss is describing as a poorly named bit of mathematics, right? It sounds like he's saying, it sure is a shame that they called these imaginary numbers. And I'm feeling like, yeah, I agree, because it totally led me to think there was something less real about them than all the other numbers. Yeah, he's throwing a lot of shade on Descartes here, actually. You know, Descartes had this habit of giving things names. So here's another one of his things. If a root to a polynomial was negative, he called it false. He didn't even call it negative. He just called it false. So I think Descartes, although he did a lot of great stuff for us, I think, therefore I am. Yeah, I think Descartes, who, by the way, was known not to get out of bed until 11 in the morning on a daily basis, should have gotten up a little earlier and put a little more thought into his naming conventions. Well, speaking of throwing undue shade, Pete, I remember that when we lived together right after college, I used to have to wake you up at 11 when Jerry Springer was on. It's true. I did fashion myself to be a young Descartes back in those days. I do feel like this episode requires a disclaimer that says that we do not watch Jerry Springer anymore. That was when we were younger and perhaps a bit dumber. No perhaps, and a lot dumber. I'm starting to get that the complex numbers aren't nearly as mysterious as I thought they were. but it must have taken people a long time to get comfortable with them. Oh, definitely. Several hundred years, actually. Interesting. So when did people first start working with them? Is there something like an earliest example that we know of? Well, here's the earliest example I know of. And I think it would be interesting if you and I try to tackle it right here in this episode. So here's the question. Can you find two numbers that add to 10 and multiply to 40? No, I meant, can you give us an early example using complex numbers? Oh, you just wait. Trust me on this one, okay? Let's see if we can solve this problem. All right. So let's see. We have two numbers. Let's call them x and y. And we know that x plus y equals 10 and x times y equals 40. Well, if x plus y is 10, then y equals 10 minus x, right? And if I substitute 10 minus x for the y in the other equation where x times y is 40, I get x times 10 minus x equals 40. Oh, I see. It's like a quadratic equation. 10x minus x squared equals 40. Right. And we can rewrite it as x squared plus 40 equals 10x. Okay, but why did you rewrite it like that? Wouldn't it be more common to write it as x squared minus 10x plus 40 equals 0? In fact, you're right. It would be more common to write it that way, but I'm writing it the way that is much more similar to how Cardano would have expressed it in his famous book, Ars Magna. Ars Magna? That sounds like Sir Barnabas's imaginary friend. It's a book. Oh, is it? A famous one. Sounds fancy. Yeah, it's very fancy. So Ars Magna means great art in medieval Latin, and it was published by an Italian mathematician named Girolamo Cardano in 1545. The problem we're talking about here, it appears in that book, and in fact, so does its solution. And that solution is very interesting. How so? Well, the solution is based on completing the square, something listeners may be familiar with, but the equation doesn't have any real number solutions. So Cardano just goes ahead and says that the solutions are 5 plus the square root of negative 15 and 5 minus the square root of negative 15. So wait, if you take 5 plus the square root of 15 and add it to 5 minus the square root of 15, you get 10. And if you multiply those two things together, you get 40? You sure do. Wow. So is that the first time anyone wrote about the square root of a negative number? Well, I think maybe Huron of Alexandria may have written about them sometime in the 1st century. He would have done it in the context of a volume calculation for a pyramid, but Cardano's calculation was more sophisticated and more modern feeling, but he definitely wasn't completely modern or maybe even mostly modern. For example, he goes on to write, "It is evident that this case or question is impossible. Nevertheless, we shall solve it in this fashion." So basically he's saying it's impossible to do this, so let's go ahead and do it anyway. That's exactly right. Yeah. Which is actually pretty great. Well, then he tells readers that they will have to imagine the number square root of negative 15. So there's that word imagine again. And that by, quote, dismissing mental tortures, it can be shown that the product of these solutions is indeed equal to 40. It doesn't sound like Cardano was 100% convinced that these quantities he was using were actually real numbers. Oh, definitely. In fact, he referred to the arithmetic that he used in that solution as, quote, subtle and useless. So Cardano conveyed a sense of ambivalence about these numbers. Do they actually exist? Maybe. Are they useful? No. Okay, well, a few minutes ago you mentioned that Gauss really didn't like the word imaginary, but he definitely seemed okay with complex numbers. So how much later was that than Cardano's time? Well, it was almost exactly 250 years, but it still took more than 100 years beyond that for complex numbers to start showing up in significant applications. Which brings us back to the question I had at the start of this episode. How are imaginary, now that I know the terminology better, how are complex numbers actually used in real-world applications?
Well, that's an interesting question. And I want to start with a confession here. My training in pure mathematics didn't really give me much, if any, practice with real-world applications of complex numbers. In fact, I'd say I have almost no training in applications in any area of mathematics.
Oh, so what you're telling us is you got nothing.
Dude, no, come on. I do think, though, that it might be interesting for our listeners to know that the divide between pure and applied mathematics is often really pretty sharp. But I can tell you that complex numbers do show up in lots of places. And maybe my favorite place would be in physics.
Well, physics does sound pretty real world to me.
Yeah, me too. So let's talk about what was going on at the beginning of the 20th century. Einstein had just published his theory of special relativity in 1905. And 3 years later, Hermann Minkowski, a German mathematician and physicist, introduced the idea that space and time can no longer be thought of as separate phenomena. They need to be united in a four-dimensional construct that he called space-time.
Was that some sort of early 20th century version of FaceTime?
No, not really. Minkowski referred to this point of view as the world postulate. And at one point, here's what he wrote. The essence of the world postulate can be expressed mathematically very concisely in the mystical formula 300,000 kilometers equals the square root of -1 seconds.
Oh, yeah, sure, of course. Kilometers equals seconds. And not just any amount of seconds, an imaginary amount of seconds. A distance equals a time.
It's the ship that made the Kessel run in less than 12 parsecs.
That's pretty complex already.
Yeah, it totally is. Well, and then later in 1926, Erwin Schrödinger published his discovery of the wave equation. And the time-dependent formulation of this equation uses the square root of -1.
Was that a big deal at the time?
Well, here's how the physicist Freeman Dyson put it. Then came the surprise. Schrödinger put the square root of -1 into the equation, and suddenly it made sense. Suddenly it became a wave equation instead of a heat conduction equation. And that square root of -1 means that nature works with complex numbers and not with real numbers.
Well, that's very curious. And Schrödinger surely knew that curiosity killed the cat. And at the same time, it didn't kill the cat. But seriously, I can see how cool it is that he realized nature works with complex numbers. But does that also mean that nature works with only complex numbers and not real numbers?
Well, since the complex numbers contain the real numbers, I think he just meant to shift our attention to that larger set. And it's hard to know, but it may be the case that at a very deep level, the universe is fundamentally not knowable without the use of complex numbers.
Well, that is a really cool thought. I never realized before how much I kind of had it wrong in my head when I thought about what imaginary numbers even were. I imagine that lots of our listeners might have had the same misconception as well, and maybe even have more questions now. I know I do. Do you want to tell our listeners how they can get in touch with us if they want to send any of those questions our way?
Sure. Math Club, reach out to us on Twitter. Our handle is @MathClubPodcast, or send us an email. Our address is mathclubpodcast@gmail.com. Say, Noah, when this episode's done, you want to get some cheese and crackers?
Oh no, you just reminded me. Sir Barnabas, he's been waiting all this time. Sorry, Pete, I gotta go.
Bye, everybody. Bye, Barnabas.